Let us consider energy stored in the field. Now, whenever we are having field concept, something is extended in the region, spatial region. Therefore, I cannot assign energy concentrated at one particular object or point. I should have, since I associate energy with whole field, I should define how much energy there in a unit volume of the field. This concept is called energy density. Now I have to obtain an expression for energy density stored in field or energy stored per unit volume of the field. This can be easily obtained by using the concept of parallel plate capacitor. You must know the expression for energy of the parallel plate capacitor in terms of its area and distance between the plates. When a battery charges a parallel plate capacitor, the battery does work in separating the charges. I have to create charges on the plate means I have to separate them. Therefore, work goes in separating the charges. If battery has moved a total amount of charge Q by moving electrons from the positively charged plate to the negatively charged plate. Electrons are moved away from the positively charged and they are put on negative plate. Then voltage across the capacitor is V is equal to Q by C, where C is the capacitance. The amount of work done by the battery is, we know this formula, half CV square from our studies in elementary physics. The battery has converted chemical energy into some kind of electrostatic potential energy. Why some kind? Now I don't know whether that energy is with charges or stored in the field. We can view the energy as being stored in the separated charges. For example, whenever you take an object in the field of gravitation, when you lift, you store the energy in the object as potential energy. Similarly, it may happen that here energy may be stored in the separated charges. Then U is equal to half Q square by C. We can also view the energy as being stored in the electric field produced by the separated charges. This is another way that whenever capacitor is charged or uncharged, there is no field inside whenever it is uncharged. But whenever it is charged, there will be uniform field inside the capacitor. Therefore, whether that energy is saved in the charges or in the field, we don't know. We can also view as energy as being stored in the electric field itself, created by the separated charges. And in that case, I should not write it as half Q square by C, but we will write it as half CV square. Okay, potential is another way of defining field. Let the area of the plates of the parallel plate capacitor be A and plate separation be D. Then V is equal to ED. Capacitance is equal to half epsilon, capacitance is C is equal to epsilon naught into area divided by separation distance. We can therefore write half into epsilon naught into E square into A into D. And this A into D is nothing but volume of the space between the plates. This is the area of the plate and separation distance is D. Then it is something like parallelepiped and area volume will be given by area into D. Inside this volume, electric field is approximately constant, and outside this volume, electric field is almost zero. We interpret as the energy density, U divided by that volume as the energy density, the energy per unit volume in the electric field. The energy stored between the plates of the capacitor equals the energy per unit volume stored in the electric field times the volume between the plates. In electrostatics, viewing the energy as being stored in the separated charges or viewing it as being stored in the electric field leads to the same results. If you consider that energy is being stored somehow in these charges, will give us the answer energy density as or total energy as U is equal to half Q square by C. Or other way is, we can have same thing. Charges are present on the plate, minus, and there is uniform field here now. That energy may be stored in the field itself. That also gives the same answer of E square in terms of E square into epsilon naught E square. Therefore, now we have two ways of looking at potential energy stored in the case of capacitor. One is charges themselves, they have the energy, or else field has energy. In electrostatics they give the same answer, but in electrodynamics or whenever fields are varying, it is better to think that energy is stored in the field. Therefore, we will have this concept consolidated, that energy is stored in the field itself. Now let us consider what happens to energy when two capacitors share their charges. Initially, here is a capacitor with C1 and charged, therefore it will have certain voltage V1. Another capacitor, it has capacitance C2 and it is also charged, therefore it has a voltage V2. Now when we connect them, they will come to same voltage, which may be different from V1 and V2 because of there will be sharing of the charges. Now what happens to energy, I have to discuss. Consider two capacitors, our capacitances C1 and C2 charged to potentials V1 and V2. When they are joined by a wire, they attain a common potential V. That potential is given by V is equal to total charge divided by the effective capacitance or total capacitance. And what is the total charge? If C1 and V1, then initially charge is equal to their product C1 Q1, and here Q2 will be C2 V2. Therefore, total charge will be C1 into V1 plus C2 into V2 divided by C1 plus C2. The total energy of the two capacitors before contacts is nothing but energy stored in the capacitor, that is half C1 V1 square plus another capacitor's energy is half C2, this should be C2 V2 square. The total energy of the two capacitors after contact energy is given by effective capacitance into final voltage, half C1 plus C2 into V square. Substituting for V1 from here, I get this expression. Therefore, after doing some mathematics, you will find that final energy after sharing is half into C1 V1 plus C2 V2 square divided by C1 plus C2. Difference in the energy before and after sharing is Ui minus Uf, and that is given by this expression. If you do all the necessary arithmetic or algebra, and you will find that final expression is C1 C2 divided by 2 C1 plus C2 into V1 minus V2 whole square. Now you write like this: Ui minus Uf is equal to this much. That means whenever V1 is greater than V2, this term is positive. Even if V1 is less than V2, then also this square term is positive. Therefore, this Ui minus Uf is always greater than or equal to 0. Loss is positive. That means we will have some energy lost after sharing. What happens? Where that energy is going? The sharing of the charges occurs when we connect through the wire, and wire has some resistance, therefore current flows, there will be Joule heating, or else it may occur due to the sparking also. In that case, energy appears as partly as light or sound. That energy lost goes as heat, light or sound.